Good morning to everybody. Today we are going through the lecture number 3, remote sensing, of course. And today we are facing a very important topics that is dealing with the interaction between electromagnetic energy and surfaces, in particular Earth's surfaces. All right. Let's start with this kind of interactions. And as mentioned in a previous chapter, the radiance L is the most important of the physical quantity in remote sensing because in fact it is the primary measurement quantity of the interaction processes between electromagnetic energy and the surfaces. So that means that what the sensors that are mounted on board of a satellite platform are measuring is essentially this radiance L. The whole process of interaction with surfaces follows, as we saw in the previous lecture, the principle of conservation of energy, expressed by the Kirchhoff relation, whereby, as we know, the sum of the three coefficients, rho, that is the reflection coefficient, alpha, that is the absorption coefficient, and tau, that is the transmission coefficient, is equal to 1. Um, and these three coefficients, of course, they are representing, taking into account the total quantity of energy that inside of a particular surface, they are representing the fractions of reflected, absorbed, and transmitted energy, of course, with respect to that incident. All right, it is evident that for opaque bodies in certain spectral intervals, and this is happened for the most part of our sensitive experience, the value of tau, the transmission coefficient, is of course zero, or in any case negligible. So the components of the balance are reduced to that of reflected energy rho and absorbed alpha. So that means that usually, as coming from our experience, for example, just looking at a wall or a table or many of the surfaces we are using, apart from glasses, for example, most part of the surfaces in our real experience are to be considered opaque. So that means that, as mentioned here, the transmission coefficient is negligible. But when we are observing Earth's surfaces from satellite, considering as we will see that the satellites is very far from the Earth's surface, most part of the surfaces over the Earth are to be considered as our single experience as opaque. If they are opaque, that means that we can take in read of the transmission coefficient, having only to deal with two coefficients, so the absorption and the reflection coefficient. That is very, very important because if we have only two of these coefficients, we can simply stay just, observing our images acquired from satellite that if we are facing a cell that is very bright over these satellite images, that means that the surface that is represented in this cell of the image is reflecting or emitting energy. So that means if they are reflecting energy, if it's reflecting energy, that means that the rho coefficient is quite high. On the contrary, if the cells are quite dark, that means that the rho coefficient is very low. If the rho coefficient is very low, considering that most part of the surface, almost all of the surfaces, as observed by the satellite over the Earth's surface, are opaque, if the reflection coefficient is low, so the cell is dark, that means that in that case, for that surface, in that spectral band, it's prevailing the absorption coefficient. So having only two of this coefficient is quite easy to understand the interaction. While if we have three coefficient, in the rare case on the Earth surface of the presence of the tau coefficient or the transmission coefficient, and we will see that before, especially for water. Having to deal with three coefficient, it's very hard to really understand which one of the three different behavior is prevailing in our image. So recalling that, I'm sorry, the energy absorbed serves to thermally charge the body in question and then trigger the phenomenon of the emission of electromagnetic energy, regulated in turn by the emission coefficient epsilon. The radiant flow that is coming from a generic surface substantially includes the contribution of two components, that of the reflected energy and that of the energy emitted. So considering that we can also face this, look at here, this epsilon coefficient that we will introduce that afterwards, is a sort of emission coefficient. So the ability of a particular surface to emit energy. Also, the epsilon, it's a coefficient, so it's ranging between 0 and 1. And when we have, as is written here, a radiant flow that is coming from a surface, we just state that this flow includes these two components, different components, part of reflected energy and part of emitted energy. Okay, let's talk now about specular and Lambertian surface that are very important. And this is part of what we can consider as the geometric interactions between the energy emitted by the sun when striking over the Earth's surfaces. So specular surface is defined as a surface whose observed radiance value, that is the L, that is, it's ranging with these two particular angles that are theta 1 and phi 1, and we will see a figure to better understand these two angles, is reflected in one specific direction, where these two angles are the same. Lambertian surface is defined as a surface whose observed radiance value is constant for any combination of geometry between the source and the observation point. This surface takes on the meaning of integral diffuser and, like the black body, it's only an ideal model. So, stating these two first definition, in real case, we can consider the surface from the geometric point of view similar to these two ideal models. So the specular model and the Lambertian surface. The Lambertian model came from Lambert, that was a very famous French physicist. Okay, a good approximation of the specular surface can be a mirror, while for a Lambertian surface can be, for example, the screen of the cinema. So consider these two examples in order to generalize this behavior. The mirror, of course, is something that is very similar to the theoretical behavior of a specular surface. So, you can observe your figure reflected over a mirror only when you are more or less perpendicular to this mirror. Because if you are placed in a divergent position, just for example, looking your mirror on the left side, you will not you will not see your figure reflected simply because the reflection will go to the direction that is, something that dealing with this angle in which you are placed. While for the Lambertian behavior, just to make you easily understand, you can think about this screen of the cinema, or simply when we are in a class at the university, just the screen in which, for example, we are projecting out of a computer. These screens are acting like the Lambertian surface, because no matter which is the position in which you are watching what or is displayed on the screen, from every single position, also from a very inclined position, you can see what is displayed. So that means that the reflection that is coming out from this screen is independent from the incident angle of the source of illumination. So if I'm projecting over a screen a flux coming, for example, from a video projector, and this video projector is perpendicular to the surface, if this screen is a specular surface, you can see what is projected only if you are in the same position of the projector, because if you are projecting perpendicularly, the reflection will be perpendicularly too. While if you have, as in the reality, a screen that is acting like a Lambertian surface, you can stay in whatever position and you will see what is displayed over the screen, because the reflection is independent from the incident angle of the electromagnetic source. In order to better understand these things, we can see these two very simple figures. On the left side, you have what I mentioned concerning the specular reflection. You see, we have an opaque material, for example, a mirror, and this is very important, because if this surface is opaque, as we mentioned before, the transmission coefficient is negligible, or better, equal to zero. And then we have this red arrow that is the electromagnetic flux that is insiding over the surface. And the angle, the incident angle, is this I value, look at here with the mouse here, that is evaluated, taking into consideration the orthogonal direction with respect to the point of incident. So this angle I is this kind of angle, the inclination of the electromagnetic flux, and the perpendicular to the point in which you have the incident flux. Then for a specular surface, you see that the reflection is going in one precise direction with respect to this angle r, where r is equal to I. So that means that you can see, for example, here is the idealization of our eye. You can see this flux, for example, is indivisible only if you are on that direction. All right? While for the diffuse reflection, that is another way to mention the Lambertian surfaces. If you have this opaque material, okay, and you have the same fluxes with the same angle of incidence the reflection, you see, is going in all the direction. Of course, only on the upper hemisphere, because this surface is opaque, so we don't have any transmission coefficient. So no matter where you are placing to watch this particular flux, if it's indivisible, you can stay in every single position of the upper hemisphere and you will see something that is reflected. All right? This is very, very important, because taking into consideration this particular figure, okay, and going to the specular reflection, in the very first lecture, we mentioned the fact that usually the satellites are acquiring these images, this radiance that is coming from the ground, being perpendicularly to the surface. So the satellites are in that position. So if we are facing and the sun usually is for most part of the acquisition over the Earth's surface is not perpendicular at all. So I mean, in general cases, the sun has a different angle of incidence than the perpendicular one. So if you have the satellites here and the sun here, if you are facing a specular surface, I mean, this surface can reflect energy. So that means that this surface has a reflection coefficient that is bigger than zero. But I mean, if reflecting, is reflecting in a divergent position than the satellites that is carrying on board the sensor. So I mean, the sensor cannot register anything of the radiance coming from the surface just because, I mean, the surface is acting as a specular surface. While in the opposite case, if you have a Lambertian or a diffuse reflectors, if you have your satellite here, if the surface that is insided by the flux coming from the sun, I mean, if it's acting like a diffuse reflectors, I mean, if the reflection coefficient of the surface is larger than zero, okay, part of these fluxes for sure will strike over the detectors of the sensor mounted on board of the satellites, and so the satellites will will acquire an energy source. All right, so let's go. The phenomenon of reflection is governed by the physical characteristics of the surface involved, so that there is a double behavior as previously anticipated. So specular in the case of very smooth surface, and this is very important. So when the surfaces are really, really smooth, I mean, they can act like a specular surface. Imagine like a mirror. In that case, and Lambertian or diffuse surfaces, in the case of surface with a certain roughness. In both the cases, the outgoing radiance will be regulated by the anisotropic and isotropic model, respectively. So let's take into consideration this very qualitative figure. So you see that in order to face the real cases, you can have a specular reflection when you have a very smooth surface, all right? When you can have a Lambertian or diffuse reflection when you see you have something that is very rough, where all this roughness is contributing to the reflection of the energy or the electromagnetic flux that is insiding over the surface in all the direction. All right, so this is the geometrical model. So in order to apply these things to our cases, to the remote sensing cases, the separation between smooth and rough surfaces depends on the scale of analysis. Indeed, a good criterion of distinction can be that of Rayleigh, according to which the limit of smooth surfaces is defined by this relation. So we have this criterion that is called the Rayleigh criterion, in which you have this simply relation, where if H is less than this ratio between lambda and 8 times the cosine of theta of the incident angle, you will have something that is smooth. Okay, so let's take into consideration what are these different things. So H is the maximum height discontinuity of the surface. So it's the minimum height and the maximum height. So how is the altitude difference in the surface, in the z plane, of course? Lambda is the, the incident wavelength, and of course, we don't have to mention 8 cosine. Theta is the angle of incidence. All right? So let's consider our cases. So if you are taking into consideration the optical windows, you remember from the last lecture, I mean, in the optical windows, when we are dealing with ultraviolet, visible, and infrared spectral bands, lambda is very, very small. Lambda is part of microns. For example, in the visible, lambda is ranging between, I'm sorry, zero point 0.4 and zero point 0.7 microns. So it's very, very small. And considering that the theta, the angle of incidence of the energy, that in the real case is the altitude of the sun over our normal to the point in which we are considering the incident, the incident flux. I mean, this quantity here, in this part here, is of course part of unities. I mean, 8 times the cosine that is ranging between 0 and 1. So that means that it could range between 0 and 8. So I mean, this quantity where lambda is governing this ratio, I mean, is very, very, very small, all right? A fraction of microns. While h, as we mentioned before, is the maximum 8 discontinuity. So consider our images. Our images, as you will, as if you are have already saw during the labs, or you will see for the labs, are images that have a very different geometric resolution. But what we took into consideration in the first labs are something that has a resolution of ranging from 15 to 30 meters, 30, usually, all right? So consider an acquisition over the Earth's surface with a single cell of 30 by 30 meters. Of course, no matter with which area we are acquiring, of course, there will be difference in heights of part of microns, of fraction of microns. So if it's true, I mean, that means that taking into consideration the Rayleigh criterion, all these surfaces in the optical windows, whatever surface in the optical window we are acquiring from satellite, it's of course rough. If it's rough, it will act, it will behave like a Lambertian or diffuse surface. So it will reflect energy if, of course, the surface has a reflection coefficient rho bigger than 0 in every direction of the upper hemisphere, considering that the surface is opaque. So this Rayleigh criterion is very, very important because is considering that every surface over the Earth is acting like a Lambertian surface. But consider also the facts of our real life. In our real life, apart from the fact that not all the surfaces are really opaque, for example, a window is not opaque, a glass is not opaque, but for all the opaque surface, apart from really the mirrors, all the other surface, I mean, are following the same example. They are all Lambertian surfaces. How we can understand, because it's really hard to think about that. So consider a wall in your home. I mean, a wall in your home is of course a Lambertian surface, because I mean this in this case for the Rayleigh criterion, of course. I mean, it's not this quantity. I mean, the lambda that is in the visible, because we are looking at the wall with our eyes. I mean, will not be larger than that thing. So also, if it's very difficult to imagine that, But you have a proof that can, certify this affirmation that I'm doing. So, for example, if you are looking your wall, for example, I don't know, a whitish wall, I mean, you can see this wall whitish from every single position you are observing that wall. So that means that if it's always whitish or always of the same color, I mean, that means that it's acting like a Lambertian surface. And this is true for the most part of our surfaces, most part of the opaque surfaces. In our daily experience, in our real life, in the visible, from zero point 0.4 to zero point 0.7 microns, all the opaque surfaces we are interacting are for sure Lambertian, apart from, for example, the mirrors that are not Lambertian, but they are specular. But these kind of surfaces are a minority of the general surface we are facing in our real life. All right. More generally, we can say that if the discontinuities show that this quantity h is bigger than lambda, the surface can be considered rough, as I mentioned, and therefore that is a diffuse reflection. While in the opposite case, when h is less than lambda, the surface appears smooth, and there is a reflection of a specular type. So it is really evident that a surface can take on different aspects as a function of lambda, because it's lambda that is governing this Rayleigh criterion. For example, a desert sand may appear rough due to the short wavelengths in the visible or in the near infrared and be smooth in the microwave region. So you see, I mean, also the fact that the surface can be rough or smooth is depending on lambda. So another things that is ranging with lambda wavelengths is again a variable of the problem. So the same surface can be rough in the visible, for example, and can be smooth in the radar bands where we are facing centimetric wavelengths, in which, of course, in this case, in the deserts where we have very flat surfaces, I mean, these surfaces can be specular reflectors for example, in the radar acquisition. So I mean, there's another behavior that is depending of the wavelengths. Obviously, the reality that surrounds us is mostly composed of surfaces that behave in a composite mode, of course, without the clear prevalence of one of the two types of reflection, so that the final results, in addition to including mixed situation, produce anisotropic reflectances that is variable according to the direction. Of course, in the real case, I mean, we can see better the wall in a particular view with a particular view angle. But I mean, it's a Lambertian surface with a prevalence of reflection in particular direction. So I mean, as is stated here, I mean, in the real life, surfaces have a mixed situation that produce anisotropic reflectances. In the case of acquisitions made with multispectral sensors placed on board of satellite platforms, which orbits at altitudes higher than 400 kilometers in the real case, we consider the wavelengths of the visible and infrared, as I mentioned before. H is always greater of lambda, so all the surfaces are to be considered rough and therefore Lambertian or diffuse reflectors. That ensures that the sensor always receives the fraction of the reflected radiant flux, and that therefore the failure to record this flux is characteristic of surfaces framed with an absorption coefficient alpha equal to 1. That is the example of black bodies for such wavelengths, so where the black bodies are ideal bodies that are absorbing all the incident energy. in the hypothesis, of course, of opaque surfaces, because if they are not opaque, I mean, we cannot affirm these things here. This last statement, given the variability of the reflectance coefficient rho with respect to the wavelengths, does not apply to all incident lambdas, wavelengths, especially for long wavelengths that are the microwaves, that is the longer wavelengths we are using to acquire data, images from satellites. Surfaces that are opaque in the visible and the infrared, they can become smooth and therefore behave like specular reflectors, as I mentioned before, for the sands of a desert. This means that the sensor may not record some component reflected due to the divergence between the position of the sensor itself and the angle of reflection of the mirror surface, as I showed to you before when we face the two figures of the reflected and diffuse reflection. In such cases, therefore, the absence of reflected flux recorded by the sensor could mean both a surface with an absorption coefficient equal to 1 and surface with a reflection coefficient bigger than 0, which however reflects in a direction diverging from the sensor, of course. So now we have finished the introduction of the topics related to the geometry of the surfaces. And now we are taking into account the other kind of interaction that we have between the energy that is coming from the sun, the electromagnetic energy that is coming from the sun and the Earth's surface. That is the interaction that is related to the spectral characteristics of the surfaces. And in this case, we are taking into consideration these spectral signatures. Spectral signatures that are of fundamental importance for remote sensing are the representation of reflectivity variation as a function of the wavelength of the reflected electromagnetic energy for homogeneous surfaces. So, as an example, the following figure shows the spectral signature of some types of surfaces. So you see here again another diagram where in the x-axis we have wavelengths in microns. So you see here we are ranging from 0.4 to 2.4. That means that we are ranging from visible to mid-infrared. And here on the y-axis we have a percentage of reflectance, in this case ranging from 0 to 60. And I mean, this percentage could be also expressed from 0 to 1 as the reflection coefficient of the surface. And you see in different colors here, we have the spectral signature. So that are the curves that are display the behavior of the surface, of the reflectivity coefficient of this particular surface over different wavelengths. So for example, you see here when we are, I'm sorry, when we are taking into consideration the water here, for example, the blue one, I mean, the reflection is very low for all the bands. And you see that away from the visible, the surface is a very good absorber. Like, for example, if you are taking into consideration, this is a clear lake water, for example, as mentioned here. For example, for the turbid derived water with sediments, you see that the water is a very good absorber in all the different wavelengths. Here is the reflectance. So if it's not reflecting, it's absorbing energy. But you see that the turbid water is reflecting more in the infrared, in the near infrared. Well, you see, for example, here we have with these two orange and let's say maroon uh, uh, spectral signature. We have soil. Soil in remote sensing, the term soils means soil that is, I mean, there's no vegetation over this particular terrain. And so you see that this soil is reflecting very low quantity of energy in the visible, then it is have a bigger reflectance coefficient in the near and in the mid infrared. And this is the situation of wet soil with the 20% of water comprising it. If we have the same soil with less water, you see that the reflection is bigger. So I mean, this is explaining something that we can affirm generally for remote sensing, that the water is a good absorber of energy. So also if you have other surfaces, for example, soils, with different quantity of water in it, that means that the water will contribute to a bigger absorption of energy and so to a less reflection. Well, for example, here, this is the spectral signature of vegetation. And you see, for example, that if we are in a phenological active cycle, so for example, if we are in spring or in summer, and we are observing green vegetation, you see that in the visible, we will have a peak in the green bands, of course. If appears to our eyes the vegetation to be green, of course, is reflecting much in the green, while it's absorbing in the red band here, you see, look at the mouse, and then the vegetation is a very, very good reflectors of energy in the near infrared. You see, in the near infrared is reflecting much energy, much more than in the visible, and then in the mid infrared is absorbing energy. Again, is reflecting less than in the near infrared. So out from this graph of spectral signature, we can affirm two general things that are always true. The first one that I mentioned before is that the water is a good absorber of energy. The second one is that the vegetation is the best reflectors of energy in the near infrared. When we are taking into account the different spectral signature and we saw some generalities, some basics concerning the spectral signatures, now we can go in through two particular spectral signatures that are very typical and are very useful in order to better understand the remote sensing process. In particular, what is very interesting is just to see how the water and its different metamorphism, that means snow, ice, gas, and whatever, is reflecting energy in the different wavelengths of the electromagnetic spectrum. Well, among the most recognizable environmental categories in remote sensing, water and its solid state play a special role. This on the basis of their specific behavior, which in the different parts of the spectrum generally contrasts with the other elements of the landscape, and also because water is the more frequent surface that we can find on the Earth. When observed in small quantities, pure water is a substantially colorless element, of course. When you have water in a glass, of course, it's colorless, which justifies its very low reflectivity and high visible transmissivity. In the observation of a water body, it is necessary to consider the different contributions that make up the outgoing radiance. In fact, the emissivity, the flux, the electromagnetic flux coming from the sun, or that is the direct solar irradiance, together with the diffuse one due to the emissivity, irradiance coming from the sky that is caused by, you remember, the selective scattering, is in the impact of a water surface breaks down according to different interaction mechanisms. A scheme of such interactions is represented in a simple manner in the following figure. So, for example, when we are going to see this particular figure, you see, I'm sorry, this is part in Italian, but omitting the dependence on the angles of illumination. So we are not really interested on the incident angle of this irradiance, this radiance, this electromagnetic energy that is coming from the sun. This radiance value that is coming, and I mean from the sun, and this is observed and acquired by an instrument that detects a surface of water, is composed in four main components defined by the following equation. So I mean, when you have this energy that is coming directly from the sun and directly here from the effects of the scattering of the atmosphere, so is going here to the water surface, an observer, here we have our eye, but could be, of course, a sensor mounted on board of a satellite platform. In reality, what is coming to our eyes, for example, is composed by four different components. This is the radiance that is coming from the atmospheric scattering, that of course is not coming from the surface, but it's coming from the tropospheric layers. Then we have the reflectance that is coming from the surface of the water. Then we have the reflectance that is coming from intermediate layer of the water. And then at the end, you can also have this quantity that is the L seabed that is coming from the seabed of the water. Of course, this lambda, that is the water, the inside layer of the water and the seabed, this condition that of course is changing our idea of having only opaque surfaces where the transmission coefficient of course is null or is negligible. For this kind of particular surface, the water, that could not be true. And this is the only case of surfaces on the Earth's surface that are not really opaque. But pay attention that what I'm saying here is only true when you have a very thin layer of water. So that means that from satellite, for example, at more than 400 kilometers altitude, a sensor is getting also the water as an opaque surface. So without any energy that is coming from the middle of the water and from the seabed. This is true only when we are taking into consideration only thin layer of water. That means very few dozen of centimeters. This is, for example, real in lagoon, for example, and in Italy we have very large lagoon just close Venice, in which, for example, from the satellite, you can also take and you also catch energy coming from the seabed. But this is true only for this very thin layer of water, or just close to the coast of the sea coast, for example. When you have really, I mean, 20, 30 centimeters of water, not more, because for some meters, the water became absolutely opaque. Anyway, at the observer, what is coming in general terms from the water is the sum of these four different components. So the atmosphere, as I described, is coming from the Rayleigh scattering, or if we have, for example, a cloudy day, is coming from non-selective scattering. So this sort of grayish tone. The reflectance that is coming from the surface is, of course, due to the effects that in general terms, also when we have a larger and not so thin layer of water, the water is opaque. So what is reflecting is the surface of the water. Then we have the inner layer of the water when it's not so, when the layer is thin, as I mentioned, and then the seabed, of course, only in particular conditions. So in any case, the components of the previous equation, different from L, the water, what is coming in the middle of from reflectance of coming from the middle of the water, the most important information needed turn out to be disturbance and undesired. The most arduous task of aquatic remote sensing lies precisely in isolating the radiance of interest from these components, because, of course, if we are interested in understanding the characteristics of the water, of course, what we are interested in is the reflectance that is coming from the inner layer of the water, beyond the surface, and not from the seabed. But this is very hard to take, because you see, for example, when we are taking into account, for example, you see here only more or less the visible plus the UV in this diagram. These are, of course, spectral signature limited to the ultraviolet and all the visible. Here, for example, you see you have the spectral signature of the surface layer of the water. Here you have the spectral signature of the inner layer of the water, while here you have the reflectance that is coming from selective scattering. So what we are interested in, especially when we are studying water, is this layer, these intermediate layers. But trust me, it's really tricky to separate this particular spectral signature, and this is difficult to separate that from remotely sensed images. But we will try also in the labs to have some more clear idea concerning the reflectivity of the water. The portion of energy reflected by the water, in any case, when it's poor, can reach a maximum of 3% of the incident radiant flux, and is confined mostly to the bands of blue-green light, from where a continuous decreasing is observed going towards the length of longer wavelengths, until completely absorbed already from the near infrared. And for example, it's quite clear, you see here in the previous figure. So we have more reflectance in the blue and the green band, especially from the surface of the water, because it usually is reflecting the color of the sky that is bluish if it's not cloudy. And then you see that just in the red and then in the near infrared, the water is a very good absorber of energy. So it's not reflecting really nothing, because it's absorbing all the energy. The color of the water, therefore, is not as all the other surfaces, and as I mentioned before, is not an intrinsic property, but depends almost exclusively on the influence of the surrounding environment, such as the color of the sky, of that of the seabed, and the results of the diffusion caused by the presence of compounds, such as phytoplankton, suspended sediment, and the organic component of other substances. Snow and ice that are the solid state, another metamorphism of the water, represent the solid state of water, and their high reflectivity value is one of the most important features in Earth observation. So it's very easy to understand also for beginners that snow and ice appears to our eyes very whitish. So that means that they are reflecting very much in the visible bands. What we are not really used is to understand how these particular surfaces are behaving in other spectral bands than the visible. But due to the fact that there are parts of the Earth that are always covered by snow and ice, just to understand these properties of the reflection for these metamorphisms, for these solid states of the water, is very important for remote sensing. The snowpack is made up of a series of superimposed layers of snow, that is snowfall or wind deposits, and have different physical and mechanical characteristics depending on their state of metamorphism. In the case of dry snow, snow with a temperature that is less than 0 degrees Celsius, the evolutionary processes of the snowpack can lead to the rounding of the faceting of the crystals. And you know that the crystal of the snow are a very singular form that is a sort of fractal. When, on the other hand, due to heating, the snowpack increases the snow temperature up to 0 degrees Celsius, the fusion processes that take place led to the formation of wet crystals. The optical properties of the snow cover in the visible and near infrared depend on some specific factors of the composition and structure of the snow and its metamorphisms phase. Among these, the size of the crystals, the thickness of the mantle, the density, the presence of impurities and content in water. The reflectance of the fresh snow is very high in the visible and in the near infrared, and decreases strongly in the medium infrared, giving rise to well-distinguishable absorption structures at wavelengths greater than 1 microns and in correspondence with the water absorption bands in 1.4, 1.9, and 2.6 microns. And this is shown in the following figures. So you see here, again, we have spectral signature. On the y-axis, we have wavelengths that ranges from blue to, let's say, near infrared. And here you have the reflectance value, so the rho coefficient ranging from 0 to 1. And you see that the fresh snow appears to be white till here. And so with the same maximum amount of reflection for the blue, green, and red band. And then you see it's also very reflective. You see here till to 0.6 here in the worst case, also in the near infrared. In fact, in the labs, you notice or you will notice that when we are facing snow, this snow is very reflective, so it appears very bright, also in the infrared bands. But you see that for fern, glacier ice or dirty glacier ice, you see that they appears to be grayish, white here for the fresh snow, and grayish but bright for the glacier, and let's say very dark but grayish for the dirty glacier ice. But you see that we can distinguish the different metamorphism of the snow just taking into consideration this particular spectral signature. Another very important spectral signature is the spectral signature of vegetation, as I mentioned when we started this topic. Because the spectral reflectance curve of vegetation is frequently indicated in remote sensing as the spectral signature par excellence. Its shape in the different wavelengths depends by the different factors that we are analyzing below. The first factor is related to the leaf pigments. The portion of energy reflected in the visible field is related to the presence of leaf pigments such as chlorophyll, xanthophyll, and carotene. Chlorophyll in particular, that is representing the 65% of the overall pigments of the leaves, is responsible for the two absorption bands in blue and in the red, and the maximum relative reflectivity in green, according to which the plant works. This effect is due in particular to chloroplasts, which contain granules where the different types of chlorophyll are located. Carotenes, on the other hand, impart those yellow-orange tones to poor or chlorophyll-free leaves. So that means that, due to the fact that on the leaves we have these chlorophyll pigments, the chlorophyll pigments are absorbing mainly the blue, but especially the red part of the visible in order to start the photosynthesis. So that means that, if you want I'm sorry, the photosynthesis starts, well, you need to have red light just impacting over the leaves. And this is why we have this peak of absorptions in the blue and near the red bands. And you have the green part of the spectrum that is mostly reflected. And for our eyes, the vegetation usually, if it's green, depends, of course, from the fact that it's reflecting most the green part of the visible spectrum. The second particular parameter that is involved in the reflectance, in the different reflectance and in the spectral signature of vegetation is related to the leaf structure. It is responsible for the spectral behavior in the near infrared bands between 0.7 to 1.35 microns. By leaf structure in this context, we mean the spatial organization of leaf cells with reference to its morphological evidence, which varies from one species to another. So, you can also differentiate in these particular spectral bands different species of vegetation. Infrared radiation does not interact with chloroplasts, but is greatly influenced by the structure of the leaf, which causes a very high reflection of the order of 30 till 70% of the incident energy. The portion of residual energy is mainly transmitted. That is very little. So what is very particular for vegetation is that due to especially the leaf structure, the near infrared band of the inciting energy coming from the sun is mostly reflected with very high reflection coefficient. And this is the unique surface that is present on the Earth surface that is reflecting so much in the near infrared. In fact, on the other hand, the foliar pigments and the cellulose that constitutes the cell walls are transparent, and on the other, the water contained in the leaf has weak absorption phenomena that usually is less than 10%. At the beginning of the near-infrared interval, the reflectivity passes so abruptly from a few percentage points to values close to 50%, with a steep gradient around 0.8 microns. The level of the reflectivity plateau is higher the more the tissue is made up of cells with irregular shapes and the heterogeneous content. The reflectivity and the transmissivity have similar values with a certain prevalence of the reflectivity, which can reach the limit value of 80%, as in the case of the olive tree, for example, that is very present in the Mediterranean area and, of course, also in Italy. This phenomenon in remote sensing is of essential importance because it is the basis of the most significant analysis possibility of the plant world, whereas the study of reflection in the near infrared becomes a powerful investigation tool both to discriminate different species and to analyze the evolutionary stages and to determine possible pathologies within the same community. So this is why this is why uh, this is why, for example, when you are visualizing on your software the force color composite, whatever is in red is vegetation because we have associated to the red channel the near infrared, and this is the answer to that. All right, so the third parameter is the water content. In the shortwave infrared domain, between 1.35 and 2.7 microns, the spectral properties of vegetation strictly depend on the water content in the leaf, whereas we have seen at 1.4 to 1.9 microns and 2.6 microns, we have an intense phenomena of absorption of radiation by water, while also the relative maximums of reflection and 1.65 microns and 2.2 microns are partially influenced by the water content of the leaves. In this way, the absorption wavelengths, as for soils, can become diagnostic with respect to the water stress of the plant. So you see here, we have the representation in this figure. So what we have we have just mentioned, the fact that you see in the blue here, look at the mouse, and in the red bands, we have this strong chlorophyll absorption, while in the green band, we have the relative peak of reflection in the visible. Then you see we have this is the red age, you see, when we are passing just in the middle of red and near infrared to a very high reflectivity, and this high reflectance of vegetation in the near infrared, you see, is due to the cell structure, while you see here, then the reflection is decreasing in the mid infrared, and this the decreasing of the reflection is essentially due to the absorption bands due to the water content. So this, take in mind that this is the very typical spectral, spectral signature of generic vegetation. All right. So you see here that what I mentioned before, that you see here, for example, when we have these green, orange, and violet, let's see, magenta colors, apart from this grass that is very different. But in this case here, you see that in the visible and in the just here to the red edge, I mean, these three species, so green grass, deciduous, and conifer, that are the last two are both trees, they are reflecting in the same way. So in the visible, that appears to be very similar. But you see that when we are taking into account the infrared, especially the near and the mid-infrared, you see that the spectral signature are diverging. So in this particular spectral bands, you can also recognize different species of vegetation. From the emissive point of view, the vegetation behaves very differently depending on the water content, as demonstrated in the examples. And these are the examples. From the diagrams, the emissivity trend of a grass lawn in vegetative condition could be assimilated to a black body. So you see that is a dry grass without any water. So it's emitting not so much energy. While, for example, with values close to the unity over the entire spectral range, you see this green grass, this one, is really emitting a high quantity of energy. While this quantity of energy is very low, is lower than before, if you are taking into consideration, for example, dry grass. And this is very important because if we are taking into consideration the emissivity, how much energy is emitted by green grass and dry grass, we can think about the possibility to separate in the thermal infrared, because you see here, we are talking about the thermal infrared when we are talking about emission, that, for example, we can distinguish between green grass and dry grass. And why is this so important? Of course, it's important for agronomy, but it's also important to understand if there are areas prone to forest fire, for example, where, of course, dry grass or dry trees are more prone to fires than the same with than the same species with lower content with higher content of water, of course. Okay, I think that for today it's enough. I mean, we described the interaction between the electromagnetic energy and the surfaces. We took into account in the first part the geometric components. So we described specular and Lambertian or diffuse reflectors. And we also introduced the fact that we can use the Rayleigh criterion in order to understand when a surface behave as a diffuse or a specular reflector. And then we pass through physical and chemical properties of the surfaces that are, I mean, they are in some way interacting with their spectral signature. And so we introduce the concept of spectral signature, and we analyze the two spectral signatures that could be generalized in remote sensing because they are more or less the same. That is water and their metamorphism, especially in the solid state, that is snow and ice. And then the end, the vegetation, just taking in particular consideration this spectral signature, because as I mentioned before, is considered the spectral signature par excellence. Okay, this is ending the lecture number 3. So thank you for your attention, and we will meet again for the next lecture. Bye bye.